Hello everyone, and welcome to our second day of the workshop Copernicus Marine for Mediterranean Sea. So my name is Gaelena Sterbik and I'm a training officer at Mercator Ocean International, and I'll be your host for today. As you know, today is the second day of this training workshop, and today is the practical session using Copernicus Marine data. So before we start, let's quickly go over some house rules and guidelines. First, we ask you to not use the chat that you see on your right-hand side for the questions. You can use it for small talk or to say hello to each other. But if you have a more technical question or content-related question, we invite you to use the dedicated Q&A section. So you will see it on the top bar of your screen. You can click the Q&A button and it will open the dedicated section where you will be able to ask the questions to the speaker. And next to it, you will see a dedicated section to the polls. So it's the survey of today. We invite you to fill it when you want. So it will be really helpful for us. And yeah, so concerning the agenda for today, we will have 4 demonstrations. The first one with Anaïs from the first day, so from the Copernicus Marine User Support. We'll present to you the Copernicus Marine Toolbox, a very useful tool to download the data. And then we will move to the 3 tutorials that our experts from Novelties prepared for you today. So we will start with the Jupyter tutorial with Alexandre Romerin, and then we will have the QGIS tutorial with Daria Andrievska, and finally the RStudio tutorial by Simon Millet. You might have already took a look to the tutorials that are available on the website, and if not, you can still do it after the webinar. So yeah, we will now start with the first presentation with Anaïs. Welcome, Anaïs.
Hello everyone. So I will share my screen first. All right. So my name is Anaïs, and I'm a part of the user support team of Copernicus Marine Service. Welcome to this presentation dedicated to the Copernicus Marine Toolbox, our official tool for downloading marine data. So the Copernicus Marine Toolbox is a free user-friendly application that connects directly to the Copernicus Marine Data Store. And with this tool, you can access complete metadata, full data sets, or only specific subsets you need, whether they come from digital models, satellites observation, or in situ measurement. The toolbox lets you select and extract only the data you are interested in optimized format without any limits on volumes or bandwidth. In other words, it allows you to explore and download everything available in our catalog with no quota restriction. So during this presentation, I will guide you through the main feature of the toolbox, and I will demonstrate how quick and easy it's to download data with it. The Copernicus Marine Toolbox has 4 main functions. The first one is the logging function. This function generates an encrypted file containing your logging credentials, so you don't need to enter them every time you download data. The second function, it's called describe. It allows you to retrieve details metadata about the chosen product and dataset. The third function is the get function. This one allows you to download the original files exactly as they are provided by the data producers. And finally, you have the subset function. This one is particularly useful if you want to extract only a part of the data. For example, for a specific region, defined a period of time or selected depth. All this function can be used in 2 different ways, either from the command line interface, such as Miniforge prompt or any other terminal, or directly from the Python and environment, such as Jupyter Notebook, Visual Studio Code, Google Colab, or any other code editor. So before going further, let me show you where to find all the information you need to install and use the toolbox properly. So I'm going to the Help Center. So in the Health Center, you have the section Copernicus Marine Data Download. So go in it and then scroll down a little to the Copernicus Marine Toolbox section. You will find there step-by-step articles covering everything from installation to advanced use cases. In the Getting Started with the Toolbox session, you will find introductory article that provide more details about what I'm presenting here, along with clear instruction for installation and first use. If you prefer not install the toolbox, you can also use it directly through a simple executable file. So this option works only via a command line, but it's often the fastest way to get started. In the main functionality section, you will find separate articles explaining each functions, both from command line and API, Python. The use case section contains a practical example on how to use the toolbox from different needs, downloading, filtering, and automating workflow across several programming languages. And finally, the troubleshooting and FAQ section include a presentation of the latest toolbox version, a list of issues and their solution, an FAQ with the most common questions from our community, explanation on the available data formats such as NetCDF and ZAR, and an article that explains how to report an issue or request for a new feature. You can also find a roadmap of upcoming improvement. So now let us move on a practical demonstration. So we will start with the command line interface using the Miniforge prompt. So I will open my Miniforge prompt here. So the first step is to activate your Python environment by typing mamba activate your CMT. So I have named my environment CMT for Copernicus Marine Toolbox. So please note I'm no longer located at my base, but rather in my CMT environment. To check the toolbox versions that I have installed, I simply write Copernicus Marine -- version. So now I have to wait a little bit because I'm on stream live. So at the moment, I'm using the latest version available, the 2.2.2. So let's us begin with the describe function. That is the only function that doesn't require login credential. It allows you to retrieve the metadata from the Marine data store. So to see all the variables option, you can simply write Copernicus Marine, the function here describe, and then -- help. So you will see the menu, the help menu. On the left, you will see the possible option, and on the right, their description. I will not go into more detail here, but you will find everything explained in the Help Center. So I will move on the logging function. So this function is create a secure identification file. So so that you don't need to type your credential each time. So you only have to do this once. In the command line, you write Copernicus Marine. Sorry, I see the bar at the bottom. It's Copernicus Marine logging. Okay, sorry for the typo. All right. So now you will then be asked for your username and password. So I will enter my username, and please note that the password is hidden as you type, so be careful. Once it's done, the identification file will be created and stored in your default directory under the folder .Copernicus Marine. So I will just check it here in my .Copernicus Marine folder. I retrieve my identification file. So now we can continue with the get function. So this function download the original data as they are provided by the producers. And let's open the help menu again to see a variables option. So I will write Copernicus Marine get -- help. The only mandatory parameter for this function is the dataset ID option, or just I for short. To show how it works, I will first search for a dataset in the Copernicus Marine data catalog. So I will open the catalog and I will select, for example, Mediterranean product, and I will select a variable I'm interested in here, the sea surface height. And then I will select the forecast product. In the description page under the dataset data access tab here, you will see all the available datasets. For each dataset, the catalog shows the time coverage. That is the period of time for which the data is available. So here I will copy the dataset ID using the copy button here, in this case, the dataset of the sea level hourly. So I will copy it. So now I'll go back to my command line. I will write Copernicus Marine get this option I for the dataset. So I will copy the dataset ID. And let's say we want to retrieve simply a file. So if I don't enter the data of the file I'm interested in here, the function will download all the data available for this dataset. So this not what we want here. So the first, the March 21st is here. It's within the variable period, so I must further specify I want the data file that has the selected date in its name using the filter option. Filter, and then I will indicate the date. So notice the asterisk at the end. That means that our additional character in this file name after the date. So if I want to choose a folder where the file will be saved, I use the option -O, which is a shortcut for the output directory option. And here I will indicate the folder in where I want to store my data. So my data folder. So now I will launch my command, and I see several little message, the version of the data set being retrieved, the part of the data set concerned, usually default, and then the download starts. So once the download is complete, go to my data folder. So inside I find a folder with the project name, then the dataset name, then the year, the month, and finally the file itself. So the file is ended here. Let us switch to Python. So I open Jupyter Notebook directly from my Miniforce prompt by typing Jupyter Notebook. So it's possible because I previously installed the notebook package on this environment. And now a page will open automatically. Now I will open a notebook. here. And the first step is to select the kernel corresponding to your toolbox environment. By clicking here and here, I can see all the available Python environment, and I will choose a CMT environment. To use the toolbox, you must first import it by typing import Copernicus Marine, like that. So let's just now look at the subset function. So this function that allows you to extract only part of the dataset you are interested in here, according to space, time, or depth. In Python, if you want to check the available option, you can type Copernicus Marine dot the function, here subset, and then add a question mark. And now you will see all the menu, the help menu, and all the option available. So the subset function can be built manually, but to avoid mistakes, it's much easier to use the automate buttons available on the online subset page or directly in the MyOcean viewer. So I will show you, I will reopen the MyOcean viewer that I will show you the last Tuesday here, and I will click on the automate button. So this button automatically generates the correct query that that can you can then copy it into your Python environment. So now I will copy the Python template here and I will paste it into my notebook. So I already import the toolbox. I will then add two additional options again, the output directory in my data folder and the output file name to give a name of my file. Here, for example, I will name it wave data, for example. And okay, so now the download starts, and here I can see the statue downloaded, and I will check into my data folder here, the name, the files. So now let's us look at two additional functions that are available only in Python, the open dataset and read data frame option. The functions open datasets works almost like a subset, but instead of downloading the files, it opens the dataset remotely. In my case, I will simply reuse the same request as before because I'm running this demo live and the connection may slow down the opening. So I will copy it. I will remove the option open output directory and output file name, which does not exist for this function. I will change the function here by open dataset. And I will store this template into variable name arbitrarily dataset. And here I want to open this dataset. So you can see here the data open in Xarray package, but it's not saved on my machine. So to do this, you can use the toNetCDF function. I then specify the name of the variable here, dataset, where I store the data, and add the toNetCDF function. And then I will specify the path of the folder where I want to save my data and give it a name like subset data, for example. Okay, so now I retrieve my data into my data folder. So the last functions available with the toolbox is the read data frame function. This is very similar to open datasets, but instead of opening the data in a X-array package, it uses pandas to display it in a data frame. This is very useful if you want to work with CSV file. However, since pandas loads everything into memory, there is a risk of error if the dataset is too large for your machine. So for this reason, it's always better to subset first. So I will repeat my previous comment here. I will just change the variable to df for data frame, and I will change the function to read data frame. Okay. So now the opening of the data may take longer than with the open dataset because this function uses pandas. And now we see that the open data in a table form. In the same way as the toNetCDF function, I can use the toCSV function to save my data in a CSV format. So I will simply type df for the variable where I store the data, df to CSV, and then indicate the path and subset data and specify the CSV format for this data. So now I will check here, and I can file my CSV format in my folder. So to conclude, please note that all datasets in our catalog are not yet available through the subset function. So to check this, I go back to the website and I will show you the user notification service. So here in the incident tab, you can see the dataset in progress of being formatted for the service subset notification, which lists all the dataset and the products, for which a subset function is not yet available. We update this notification as soon as one or more datasets from the list become available. If you encounter any problem that you cannot solve with the Help Center or our AI assistant Blue here, so you can always reach out directly to our user support team. Thank you very much for your attention.
Thanks a lot, Anaïs, for the presentation. We have a few questions for you about the toolbox. Okay, so the first one being, is there a way to find the dataset ID straight from the toolbox without going to the home page? So I think you showed it was possible now.
Yeah, it's possible with the describe function. You can simply type Copernicus Marine describe, and then you have a option where you can retrieve the data set contains keywords or variables. So check the documentation. But it's possible with the describe function directly from your command line, for example.
Okay, thanks. So yeah, don't hesitate to check the link we put on the chat for you about the toolbox to see all of the function. Okay, so next question, why is there so many Copernicus Marine Toolbox kernel on Jupyter?
Yeah, I'm testing a different version of the Copernicus Marine Toolbox on my own machine, so that's why I need to install various Python environment with different Copernicus Marine Toolbox version for testing. That's
Okay.
my job.
But yeah, for the users, you can just use the one with just CMG.
The recently, yes.
Yeah. Okay. So this one, I think it kind of goes with the question before. How often the toolbox is updated? For example, if you have suggestions for a new function.
The toolbox is updated to approximately all the 2 months or 3 months, depending of the bugs of the hero appears. And if you have any suggestions, you can contact the user support and share uh, with uh, with me or with my colleagues your suggestion for the amelioration.
Okay, thanks for the details. Yeah, for now it's the last question, I think. Is the toolbox only compatible with Python?
No, you can also use the toolbox with R or MATLAB. In the use case section the in the help center, in the section for the toolbox in the help center, you have the use case section, and then here you have different articles on how to use the toolbox with R or MATLAB. And I think with Python, there is all the application that we have uh, write article about this, but again, we make some tests and we write different articles um, about the new tools, or if you have suggestions, again, we can make tests and write articles about this.
Okay, yeah, thanks, good to know. Still more work for you to do, if necessary. Okay, so I think that was the last question for the toolbox. And yeah, for the participants, don't hesitate to check the articles or even the replay when it's available. And yeah, if you have questions, you can contact the user support, as Anais said. Yeah, thanks again, Anais, for the presentation.
You're welcome.
And yeah, have a nice day.
Thank you.
Okay, so we will now go to the Jupyter Notebook tutorial with Alexandre. Hi, Alexandre.
Hi, Gael.
And yeah, you can share your screen when you're ready.
Yes. It should be on.
Yeah, it's okay now.
Okay, perfect. So, hello everyone. I'm Alexandre Brun from Noveltis, and so today I'm going to present to you a Jupyter Notebook tutorial on this Mediterranean workshop. So for this notebook, I've chosen the topic salinity in the Mediterranean Sea because the Mediterranean Sea has its own particular dynamics in terms of salinity, as it is a quite isolated space here away from the open ocean. So you will see that it does have an influence on the salinity levels because it tends to has a higher salinity than the open ocean, for instance. And it also has particular dynamics because on the western side, we have a clear influx from the Atlantic Ocean that, well, drives the salinity dynamics in this area. And on the contrary, the eastern part is more isolated. So this is why salinity is quite crucial parameter to monitor in this region. And we will see in detail what are the potential factors and drivers that I've mentioned, and we'll try to analyze them in detail in this notebook using data from the Copernicus Marine Service. So yes, here's a brief overview of the area. So we'll be working with Python, with some of the most common libraries that you encounter in Python. You're probably already familiar with some of them if you work with Python before. So we'll be using NumPy, which is a fundamental package for scientific computing. Xarray is a standard Python library to compute netcdf files, which is the standard format for scientific data. Which is, well, the format in which most of the Copernicus Marine Service data comes. And we'll use Matplotlib and Cartopy to draw the different maps and graphs that will generate in this notebook. These libraries are pre-installed in the Copernicus Marine Python kernel in the Copernicus Marine Service Jupyter Lab. So make sure you have it activated if you're working on the Copernicus Marine Service Jupyter Hub. And with this cell, we can import all those libraries at once. So we're almost ready to go. Now I'm going to quickly do an overview on the data products that we are using in this training. So we are using the Mediterranean Sea physics tree analysis. So it's a combination from model data and observation that are assimilated within the model to improve its accuracy. There is a dedicated page that you can visit on the Copernicus Marine Service webpage, which will give you more in-depth knowledge of the product. You have access to the user manual and quality information document here. So this gives you additional information on all the variables, how the product was built, etc. Some references, and on the bottom of the page, you have some more information, practical information on the product, such as the variables that are available, the resolution, the temporal coverage, etc. So here's a summary of the information that will be the most valuable to us. So we'll be retrieving the salinity variable, so it's called SO, the seawater temperature variable, and the current components, so the horizontal and the vertical components. We have here spatial resolution, and also an important attribute is the depth level. So you can see that we have 141 depth levels in this dataset. And finally, we'll have daily and monthly data available. So we'll try to work with both of those temporal resolutions, depending on the section here that we'll analyze. And we have a temporal coverage going from 1987 to 2025. So in our case, we'll just use data on a single year. This will be enough for us in this training. And finally, you've already had previously presentation on how to use the Copernicus Toolbox to retrieve data. So this is what we are using here to retrieve the data in this Jupyter Notebook. So we're using Copernicus Toolbox with the associated Python API. So same thing, if you make sure that you're using the Copernicus Marine kernel, because that way you'll have access to the Copernicus Marine library, Python library. Then this will allow you to enter your credentials within the notebook. And once this is done, you will be able to download the data as many times as you need. In this notebook, we're using the subset function that is well detailed in the articles that were presented by Anaïs in the previous presentation. So here's a quick practical example of how to download the data for this notebook. So here we can see that I'm retrieving the salinity variable from this dataset. So to find the identifier of the dataset, go back to the Copernicus Marine Service page of the product, go to the Data Access tab, and find the variable that you need. So in our case, we want the salinity. If I remember correctly, yes, we want the monthly values. So this is the ID that you need to copy and paste in your Jupyter Notebook here. And then to find the exact name of the variable, click on Form. And here you will see that the seawater salinity is called SO. Then make sure that the start and end date times are within the temporal coverage of the product. So here 2022, we seen before that it went to up to 2025, so it's perfectly good. We're going to download the entire year. And here we are retrieving the depth levels. So we're going to this is the closest layer to the surface, and we're going up to 5,000 meters This is quite an arbitrary choice, but it covers almost all the depth levels available in the data. So I've already pre-downloaded everything, but you can see that it is quite fast to download using the Copernicus Toolbox. So we'll be ready to go right away. You can see here, seconds ago, the product was added to the to my data library. All right. So now we are ready to open the product using Xarray and explore it a little bit. So here is the Salinity product that I have just downloaded. And when you use Xarray in Jupyter, this is the output that you have when you open it. So you can take a look at the dimensions that are available. So as expected, we have 4 dimensions. We have the the geographic latitude and longitudes. We have 12 time steps because we have monthly data over a single year, so 12 months. This is also consistent. We can see here, click on this icon, we can look at a sample of the data that is available. So here for the time variable, we can see that we have our 12 values going from January to December 2022. Same thing here, can have some, take a look at a few values here, but we have more of them, so we can't look at all of them at once. And we have our depth levels. So it is here. We can also have a quick sample here. So it's 1 meter below the surface to almost 5,000 meters below the surface that we have available as layers. And finally, this is our salinity variable. So if you click on this icon here, you can display the detailed metadata of the variable. So it's indeed the seawater salinity. Here are the maximum and minimum valid values, and here is the unit, which is basically the standard salinity unit, which can be expressed as grams per kilogram of water. And here's some more global metadata on the product with references, detailed titles, and other details such as the CF convention that is followed by the netcdf files, etc. So in this first quick overview, we're going to simply look at the surface salinity at surface level, so at the first depth layer. So to do this, we can use the cell method to subset the product along certain dimensions. So here we want to retrieve the nearest level to the surface. So we're just going to use depth equal to 0 and using the nearest method. And then we use a squeeze function to make sure that the depth layer is erased and we don't have a remaining 4th dimension with only 1 level, which could cause errors in later processing. So that we can see that thanks to this operation, we have retrieved a single depth level here, and it's not expressed in the dimensions anymore. So now we have indeed surface salinity data. Now in the next section, I'm going to show you a simple map of the surface salinity over the entire year of 2022. So using this cell, I'm just going to draw a bounding box over the Mediterranean. And here I'm computing the average salinity over the entire year of 2022. So using the mean function over the dimension time. So you can see that now that I've averaged over the time dimension has disappeared from the dataset, and we only have latitude and longitude remaining. So this is all we need to draw a map. So here's a quick setup to draw the basics of the maps, like the coastlines, zoom in on the box that I've defined, and draw the geographic grid lines. And now using the P color, I can color the Mediterranean according to the salinity values along the latitude and longitude dimensions. takes some time to draw. So here's a quick overview of the average salinity in 2022. So as we could expect, there is the influx here from the Atlantic Ocean that caused the salinity to be a little bit lower in this area. And on the contrary, we have higher salinity in the more isolated zone here in the Eastern Mediterranean. So this is what I had mentioned in the introduction. So this is quite consistent with the hypothesis. So we'll try to study this regional dynamic in more detail in the next section. So now we're going to do a very simple east and west, east to west comparison. Basically, plotting the western and eastern distributions of monthly salinity in two separate box plots. So to do that, we can select subset the data set on the western side and on the eastern side. So here we're going to compute two separate data sets. So based on longitudes here, we're going to plot this part and this part separately. And now we'll draw box plots of the monthly distributions of the two of the average values over the western and the eastern parts. And we can see that the two distributions don't even have an overlap here. So this shows that the Eastern Mediterranean has a significantly higher salinity over the entire year of 2022, regardless of the season. So yes, this difference is quite stable over the year. So now in this next section, we're going to look at that in more detail and see the evolution with time over the year 2022 to see if there is a changing pattern depending on the season. So basically, I'm going to draw the same map, but this time not over the yearly average, but I'm going to draw this map for every month of the year and animate and gather these images into an animation. So this is what is done in this cell. So I'm not going to do it now because it takes some time to draw the 12 different plots. So I have pre-done it in this, whoops, sorry, here. I've prepared the 12 plots here. And they are gathered in a single animated GIF image, which looks like this once we animate it. We can see the month here. And we can see that the spatial pattern of the salinity remains stable along the year. The noticeable change that we can notice is a clear increase in salinity here during the summer, which suggests that this salinity increase is likely due to the intensified evaporation because of the high temperatures in summer. And we also have a strong local decrease here in salinity during the summer. And I would say like spring or early summer, which is most likely due to freshwater influx here, perhaps from the melting of potential snow in this area. So we can also see the influx here from the Atlantic Ocean, and the next section will be dedicated to this interface here with in the Gibraltar Strait. So for this more detailed analysis, I'm also going to retrieve currents data to see the dynamics at this interface. So same thing as before, retrieve find the currents dataset in the DK page and retrieve the two components of the currents. So if I open it, we can see we have the same dimensions. Note that in this time, I'm only retrieving data very close to the Gibraltar Strait. Same thing here. And this time, what I want to do in this section is to find the vertical profile of salinity and currents to see how the water is exchanged between the Atlantic Ocean and the Mediterranean at this interface area. So this is why I'm averaging the data over the time, longitude, and latitude to have only a vertical profile along the depth dimension here. So I'm going to subset the data over this area on the Gibraltar Strait and plot the currents and the salinity on the vertical level, on the vertical axis of the depth. And this is what we. I'm going to zoom out to have the entire graph visible. So on the left is the velocity of the water profile, so going from west to east. And here is the salinity. So here the horizontal axis is salinity, so high salinity and low salinity on the left. And what we can see is that above 100 meters below surface level, we have a clear flux of water going from the Atlantic towards the Mediterranean. And we can see that this water has quite lower salinity here. So this is exactly the influx of water from the Atlantic Ocean that we had mentioned in the introduction. And on the contrary, below 100 meters depth, we have on the contrary water going from the Mediterranean to the Atlantic Ocean. And this time, this is high salinity water that goes out of the Mediterranean. So this is quite an interesting dynamics, and this clearly explains why we have much lower salinities in the Western Mediterranean Sea, with an influx of low salinity water and an outflux of high salinity water. Next, so we have these dynamics in the Gibraltar Strait, and now we can look at how it mixes with the rest of the Mediterranean Sea by plotting the vertical profile along an entire transect here. So if you do this notebook at home, you can get creative on how you draw this transect. So here is what we've done for this notebook, but you can change it and try other curves. Takes some time to compute here. Okay. So same as before, we've plotted the vertical profiles of the salinity. So basically, it is this curve, but replicated several times along this transect. And we can see that we have still here near the Gibraltar Strait this clear separation between a low salinity layer and a high salinity layer. But then as we go further into the Mediterranean, we can see that it mixes with the water. And here in the middle of the Western Mediterranean Sea, we can see that now the transition between the surface and the deeper levels is very smooth. And finally, in this final section, we are going to look at another potential driver for salinity in the Mediterranean, which is temperature. So same thing as before, using the same product. This time we will retrieve daily salinity data. Daily because we want to compute correlations over the year 2022, but we could have done this over several years. This is just an arbitrary choice. But we need to retrieve daily temperature to have as many data samples as possible to have a stronger correlation. And well, 12 monthly values wouldn't be enough. So retrieving the daily salinity temperature, retrieving the daily temperature, daily salinity values and daily temperature values. This time we will only be looking at the surface, so we are retrieving a very shallow depth layers. Here we open the datasets, and as those two datasets come from the same product, they have exactly the same dimensions, shapes, etc. So it's very easy using X-ray to calculate the correlations between those two. We don't have any interpolation work to do. So we can use a built-in correlation function of X-array along the time dimension, of course. And now we are able to draw the correlation map here. Also takes some time to draw. And yeah, this is a quite telling map, especially for the eastern part here, where the temperature is very strongly correlated to the salinity level of the water. So this is consistent with the hypothesis that evaporation is the main driver of salinity in this area, because here it clearly tells that the higher the temperature, the higher the salinity. We can see this western part that we have sometimes positive correlation, sometimes negative. So this shows that there are some external factors outside of temperature that also influence salinity in this area. Those are more complex patterns. And we also have here in the Northern Agency quite strong negative correlation here on the contrary. So this shows that we have quite different processes at play here that explain the levels of salinity of the water. Perhaps influx from the Black Sea here that could have a strong influence, and also French water influx from local rivers. So this is something that could be further analyzed using more data. So we're reaching the end of this notebook. So if you're doing this on your own, we have prepared some exercises if you want to go further in the analysis and play a little more with the data. I'll go quickly over the beginner levels, but well, we can draw the different math that we've shown on different dates, for instance. Yes, as I said before, you can get creative with the transects that we are using here to compute the vertical profiles of salinity. You can even draw transects going further here in the Mediterranean, and especially in the center area where the local dynamics tend to visibly change here. So this could be interesting to see how the layers interact with each other in this area. And yeah, and also don't hesitate to try to compute correlation with other variables available in the datasets of the Mediterranean analysis. This could yield some also interesting results. All right, so I'm finished for this notebook. If you have any question, don't hesitate. Thank you for your attention.
Thanks a lot for the presentation, Alexandre. We have a few kudos on the chat for the notebook, and yeah, a few questions also. So we'll start with these. The first one being, could you have compared both vertical profiles from the Atlantic and the Mediterranean Sea, or the resolutions were different?
Not too sure exactly what you mean by that. Do you think I could have compared something, some data further from this on this side of the Atlantic, maybe?
I would say it's about the salinity profile, because I think you did I think it was when you showed the transect of salinity in the
Yes.
Mediterranean. So I think it's
okay.
Yeah.
Yes. It would have been interesting to prolong this transect towards the west. It's just that the Copernicus Marine Service product of on the Mediterranean Sea stops at this boundary here, if I'm correct. So yes, we don't have any data on this product outside of the Mediterranean, so I should have combined another product to have the complete transition here. But yeah, that's some further work that can be done to have a better view of the layered interaction. But yes, you would have to do some I don't know, adaptation work to do to efficiently join the two products, probably.
Yeah. Okay, thanks. But yeah, the Mediterranean product effectively end at the Gibraltar Strait, so it would have been another one. Okay, the next one, if we look the correlation between salinity and temperature over several years, do you advise to keep the daily data, or can we use data with less temporal resolution, mainly for calculation of cost?
Yes, with several years available, I think I would probably also switch back to monthly data. What matters to me in this case is to have a sufficient number of samples to have a reliable correlation results. So yes, I think for the same concern also to be able to compute that more easily because daily data over several years quickly becomes difficult to manage. Yeah.
So, for the advice, okay, so this one I can answer. Where can I download the Python script you use in the Jupyter Notebook? So on the chat where you see the live stream, we send you the link to the page where you can download the Jupyter Notebook. You will also see it on the top bar of the event page. So you just click on the Jupyter Notebook and you will find all of the Python script and also the full video demonstration of the tutorial, because today was a quick summary mainly. But yeah, that's it. You can download it whenever you want. And it's also available on the Jupyter Hub of Copernicus Marine. This one, yeah, I think it's more a comment. The Mediterranean Sea seems to be more salty than some other seas that could be warmer. Is it because it's closed?
Yes, and with what we've seen, especially in the eastern area, which has a very little influence from the Atlantic, the open ocean influx here. So yeah, this is an area where it doesn't have many interaction with fresher water. So with also the strong temperatures here, where you have evaporation as the main driver, which causes high salinity. Yeah.
Okay, thanks. Okay, so this, well, I can answer this one. So it's still about the tutorials and articles. So everything is always available on the website. So yeah, don't hesitate to check and use you can look with the search bar with keywords to find the articles you need for the tutorials or the Copernicus Marine Toolbox. We also have a few questions about the datasets you used. I don't know if you know the answer to this one. How many data points are there at Gibraltar? Is the water flow only in one direction, or it could be flowing in different directions at northern and southern parts of Gibraltar? Do you remember what was the resolution of the dataset you used?
I can show it. So here I had downloaded for this section a smaller dataset, very restricted to the Gibraltar Strait area. I haven't plotted it exactly, so I don't exactly remember how much the resolution was. I can take a quick look, but hopefully it I won't have an error and embarrass myself right now. Yeah, try to go quickly with this. Well, let's look. I think it will take too much time to yeah.
Yeah, but I think it should have.
You have the number of data points here in the 2D dimensions. And from the current, so yes, I've only looked at the eastward component because I assume that in this interface, the inflow would be mostly in the east to west direction. So I've only looked at the eastward components of the current. But yeah, you could get some more complex patterns if you look very closely, but I've just assumed that the main interesting direction would be east to west in this particular case, which is convenient because Gibraltar side is quite horizontal.
Yeah, but yeah, on the data set, you have the 4 direction. You have eastward, westward, and you also have the southward and northward
Yes,
direction.
you could totally draw
yeah.
a complete vector field here for the currents and see the direction details. But yes, for simplicity in the sake of this tutorial, I haven't done this.
Yeah. Okay, thanks. So we still have a few questions. So thanks for the interesting tutorial. Why does the transitioning in salinity and velocity happen at 100 meters below the surface?
Well, I wouldn't be able to explain exactly why this happened at this particular level. I think it's a quite common phenomenon in this particular area, but why 100 meters? I wouldn't be able to exactly tell you why, actually.
Yeah, I guess it's just the point where the salinity change in its value. Okay, so another one. So when you import the data of the Gibraltar Strait, when you're recalling the data from the website or from the previously downloaded dataset. So you used one dataset, if I'm not mistaken.
Yes.
So yeah, it's still the same.
Yes, I sent several data requests to the same dataset. So as mentioned here for the Gibraltar Strait focus, I sent a new request towards for the currents, but for the yes, it's only always from the same dataset. So here I'm sending a new request for the currents, but I think that for the salinity, I just reused the product downloaded in the previous sections, if I'm correct. So here it's the currents. I can't find the, yes, Gibraltar. Yes, I'm using the first salinity dataset that I've downloaded in the beginning of the tutorial.
Yeah.
I just subset it to the Gibraltar Strait, so within this box here.
Okay, thanks. Now we're sure. So we have another 2 questions about the correlation between salinity and temperature. So the first one being the more general one, what other factors lead to completely negative correlation between the temperature and salinity? And the other one being, could you explain why salinity and temperature have varying correlations? Physical oceanography class.
Usually it's because you have some other phenomenon that completely dominates in a very local area. I assume you're talking about this particular part here. So this would definitely deserve some further research. The hypothesis here were the influx from the Black Sea and potential fresh water here from the continents, which is what we had assumed in this area. In those other areas where we also have a lot of negative correlations, same thing. We have several patterns that we can't observe with our limited data set that we have here. We only had temperature data, but definitely here we know that we have the freshwater influx from the Atlantic that also has an influence. So when you have several factors kind of influencing the salinity, you need to compute correlation for all of them and try to assess what are the dominant ones. Here it means that temperature is not one of them.
Okay, thanks a lot. So yeah, that was it for the question about the tutorial. Yeah, thanks again for the presentation, and yeah, I think people quite enjoyed this tutorial. Okay, so yeah, now we will go do a small break before going to the next tutorials. So yeah, a 10-minute break. So yeah, feel free to grab a coffee, take a look at the polls. We've prepared a small word cloud to get to know you better. So yeah, if you want to answer that or just take a break, and we'll see you in 10 minutes. Welcome back, everyone. So yeah, we hope you enjoyed the little break, and now we will go to the QGIS tutorial with Daria. Welcome, Daria.
Hello.
And yeah,
you can hear me, right?
Yeah, we can hear you. And yeah, I was going to say you can share your screen when you're ready.
Okay. So you see my screen, I hope?
Yeah.
Okay, great. So welcome everyone. My name is Daria, as I already been introduced. I work at Novelties, and today I'm here to present you this exercise in QGIS, which is focused on long-term changes in sea surface temperature in Mediterranean Sea and its different regions. And why we are focusing on this specific problem, specific context in the Mediterranean Sea is that over the past few decades, this sea has been identified as a climate change hotspot, which is basically meaning that the region is warming faster than the global ocean on average. And it can be like it's happening on because of different reasons. And one of them is its semi-enclosed nature and limited connection to the Atlantic. So because of that, Mediterranean responds quickly to shifts in atmospheric and ocean conditions. And this is quite a problem, the rising sea surface temperatures, because they directly impact marine ecosystems, they impact fisheries, biodiversity, coastal communities, and of course, warmer waters, they contribute to more frequent marine heat waves, which can be devastating. And shift in species distribution, increased pressure, and on already vulnerable habitats like coral life and seagrass habits as well. So that's why we are interested in studying this this phenomenon, like sea surface temperature rise. For today's tutorial, I'm going to show you what I did in QGIS, but I'm not going to show you step by step because it takes a lot of time in QGIS to show every little detail. So it's going to be a bit quick, but don't forget that we also provide you a PDF file with step-by-step procedure. And also there's a video of me speaking about exactly the same with all the details, and like that you can choose which approach to follow if you prefer to have all the details explained. So for this tutorial, I used the data from Copernicus Marine Service, and the one that's been used is a Mediterranean sea physics reanalysis. And of course, the variable that was used is sea surface temperature, or sea water potential temperature, it is called specifically in this product. And it is available in hourly, daily, monthly, yearly. But what we were interested in is an yearly mean for the period of last 30 years, you can say. So in this tutorial, we're going to look at the change, long-term change in the Mediterranean Sea between 1991 and 2021. So exactly 30 years. So I'm not going to show you how I download the data because I think it's been already explained to you, and we can go directly to the project in QGIS. So first, as I work only with one product from Copernicus Marine Service, we did several little exercises, and the first one was to import the data, NetCDF data, and to see the evolution itself. So to import the data, which is in NetCDF format, most of the products are in NetCDF format on the platform. We use this plugin, which is called NetCDF to GIS, which was developed here at Novelties by my colleagues. And this is a plugin that allows you to quickly import NetCDF format files and allow to see its structure and to facilitate this import into QGIS, because in QGIS there is a default feature, tool to do that. But sometimes it's not very convenient, it's not very clear, and you don't have this, like you don't have it's not very facilitated to exactly see the dates and different levels, because SDF is a multi-leveled format. So we used this plugin. You can read about it more in a PDF file as well to see how to download it and use it. So the product, we added our sea surface temperature, which is yearly mean, and we can see that there's a lot of layers. Here, for example, it's yeah, we always looked at January, 1st of January, and we can see, for example, I'm gonna untick, and if you look at the dynamics in the sea, you can see how it changes, and while it getting warmer, you can see that it's getting more and more orange, specifically in this like southeastern area, and you can see we are still, well, warming. It is warming. With some also splashes of more bright orange colors sometimes here and along with Italy, and here closer to Gibraltar as well. And for the last is, well, in 2021, we see how drastically changed the picture between, well, let me up between 1991, for example, and 2021. We can see a drastic change in temperature in this region again. So what we wanted to see is to have two statistics, let's say, two ways of represent the change. The change of in temperature, in seawater temperature. First one is just called change because it's a difference between 2021 and 1981. So basically, we take the raster layer. These are raster layers because, well, in SDF format, and we just take like our 2021, like this one, and we extract from it 1981, and we get this picture. I will maybe zoom a bit and close up this for now. This picture, and to do that, to like extract one layer from another, we can use raster calculator tool. For that, you would need to go to this little icon of a gear. It's a toolbox, exactly what I just closed, and you can search for raster calculator, and it's going to be under raster analysis tab here. And this is a very powerful tool to use for to work with data, with raster data, and if, well, basically not all, but yeah, with majority of data which is provided by Copernicus Marine service. And the thing is basically here you have an expression which you set. For example, for the layer I'm showing to you, it is our 2021 minus 1991, like this. It also tells you if the expression is valid, if you miss some, like, I don't know, some, the name is not specifically correct or something. And then you run it, and that's what it will give you. So here you can see that well, from 0 to 2, here you can see basically the change between the 2021 and 1991, meaning that in red there are spots that means that the temperature of water increased from into 2021 compared to 1991, and blue means the opposite, refreshing, like recooling, sorry. And well, it can be due to different reasons, of course. And in white, which we also see some white or like more like neutral color, means that, well, the temperature didn't really change much. And that was the first one. So yeah, we can see the change. We can see where is our change really happening. And the second, like, metric to really see this change more in a different way, it is to look at the rate of warming. So basically, for that, we will need to compare the SST, so sea surface temperature, sorry, across 3 decades. So the first decade, 1991, 2000, the second, 2000, 2001, and third, 2000, 2010, and third is 2010, 2020, right? And like this, comparing these 3 decades, we take average of each decade, and comparing it, we can detect whether warming has accelerated, slowed down, or well, remained stable in different regions, comparing to other decades. So that is interesting to see because it will allow us to highlight the zones that are experiencing increasing climate stress comparing to other zones. So for that, you can either go to PDF file again, as I said, and have copy paste an expression to calculate, because we're going to use again raster calculator for that. This expression is very bulky. I'm not going to even copy paste it here. It's very, very big. It's not very representative. But also what you could do is calculate 3 averages. So for example, this layer, which is average between 91 and 2000. By average, I mean that all the years between were taken, were summed and divided by 10. Then the same for the second decade and for the third. And these layers are not very representative for us. We just use them for calculating our SST pace, as they call it here. And then it's calculated those layers. To calculate SST pace, we would use raster calculator again. And in the raster calculator, we would let me just probably see, it will take some time, but we will do it. So basically, the point is to see the change between the first 2 decades and compare it to the last 2 decades. Like, so yeah, like second and third and second and first. So basically it would be, let me just verify so I don't, yep. So basically it would be average of third decade minus the average of second decade. Yes, like this. But for expression, you would need some oomph. And then we compare it with average of a second decade again, minus the third decade. And like this, that would give us SST pace. And we have it here. And it's a bit different picture that we see from SST change, and it's normal because it's not exactly the same metric. And as I said, this map highlights how the rate of warming has changed between decades, and positive values that are in red. It's coming from 0.6 to minus 0.6. They mean that warming has accelerated in the most recent decade, so from 2011 to 2020, compared to the earlier ones. And negative values, they show that warming rate has slowed or even reversed. Well, not going to be reversed, but yeah. So here we can see that it actually allows us to give a more to bring more analysis to this picture to see what's happening exactly in the region. And as we want to see how the different regions are affected, we need to actually see, separate the Mediterranean Sea into smaller seas or sub-basins. And for that, we used this vector layer, which is called World Seas. And this is provided by external website, which is also explained in a PDF file. I'm not going to stop on that. And that's basically a layer that has polygons of all the seas and all the oceans. And well, I'm not interested in all of it. We only need only Mediterranean. And we do have it because we just choose these basically regions. We can choose this one tool here and just click on each polygon. Yes. No, it's sorry, it's not. It's by polygon and select feature by polygon. Yeah, like this. No, sorry. Yeah, select feature. Why doesn't want to work? Should I do that? That's bizarre. Okay, well, anyway, we can, I guess, yes, select feature by value, which will allow us to select it by the value of the polygons. And we know that each polygon has its own ID. And well, I'm not gonna go very deep to it, but I'm telling you that each polygon here in a Mediterranean Sea, it starts with 28 and then continues with a letter to subdivide by by basin. And if we just put it ID here, we can actually to choose some specific region, and like this we get our Mediterranean only basins of sub-basins of Mediterranean Sea. And what we wanted to do next is to calculate statistics to basically see for each zone the statistics of how the sea surface temperature changed. And for that, we use a zonal statistic tool. It is here. And as an input layer, we would put Mediterranean, what we chose. And as a raster layer, we would choose any of the layers what we want. And we decided to just have to just look at each 10 years, so 1991, 2001, 2011, 2021. And you just choose the layer, and then you can run and close. And also, it will create separate vector layer, which is going to look exactly the same like the one that we have right now, but the values, it will have more values inside stored in this layer. I will show you. So we need 4 dates, right? So we need 4 layers. And to do that, we can also run it as batch process, which will allow us to basically add like all 4 out dates. Well, input layer will stay the same, but the dates will change. And like this, we don't need to repeat the same procedure. Like, you know, like here you would put your input, you will run, you will wait, and then you open it again and do again, and run as batch process allows to do it quickly and just run it as a batch. So as a result, we will have these 4 layers, and as I told you, they are exactly the same. They like visually, but if we open, for example, this one, open attribute table, this basically table has all the information of the previous layer, and the previous layer, like original layer was the external layer of the whole basin, right, for the whole world. So we have a name, we have an ID, we have all like coordinates, and this little column here, which is added, is actually the one that's been added by zonal statistics, because when we chose to run zonal statistics tool, we stated that we want the mean, meaning the mean value of the whole like sea surface temperature raster, which falls under this polygon. And you can also ask for max and mean and so on, but we only asked for one, for mean, and we did for 4 of them, as I said. But to have it more like you have 4 layers, but to have only one, to have it nicely in one layer, we can have this one that's called stats joined, which basically exactly the same one. But if we open attribute table, we will see that, well, we have only we kept only name, ID, area to see it, and also mean, which, well, this mean means it's a mean of 1991, and then there's 2001, 11, and 2021, to see how the mean value changed per specific region. And to do that, we can use we can join those layers like together, and we would do it step by step. For example, we would go to this one, double click on it. Oh, where is it? Here, and go to attributes form. No, wait. I know joins. Yeah, it's here, joins. And here you can see that there is already a joined layer of 2001, 11, 2021, because I did that. You see in each one we joined by field, by name, so to like match, like in 2 layers, take like match the columns by name of the name that's in this line. And yeah, and like here you can see that I put the custom field name prefix to highlight that it's going to be for 2001, and the same here. And to do that, you can always click on here and add exactly like join whichever layer you want with a different field. And when you set on join fields, you can choose which one to keep. And for example, me, as I told you, in a stats join, we kept name, ID, and I think, yeah, area, and yeah, and then of course it joins this mean value as you wanted. So yeah, that's it. And the last very quick I can show you is how to plot data. To plot data, well, QGIS is not very nice for plotting data. Actually, it's not made for that specifically, but we can use this tool. It's called Data Plotly, and this I already have a plot here. Great, and this tool is a plugin actually, and it's not a default plugin. Sometimes it is already installed in your QGIS when you download QGIS. Sometimes it's not. So if you don't have it, you just go to plugins here, manage install plugins, and you search for where is it? You search for Data Plotly. Oopsie. Data Plotly, yes, here. Sometimes it is already there, so you just click on it so to like show it on your toolbar. And sometimes it's not, so you just install it. It goes very quick. And here you can do different plots. And we decided to have plots on a stats joined, as I told you. It's a point plot with let me, yes, here you have a for X field and Y field and the plot itself. So here you can see the zone. So each zone is a subbasin of Mediterranean Sea. And here you can see the mean ancestral temperature for 1991, for example. And you can see the scatter plot that shows you. And if you like navigate, like hover over the point, you can see that it tells you exactly specific like number. So here it's only for 1991, and you can see which areas are, for example, Eastern Basin, as we already saw, is actually the hottest one in 1991. And if we look at the other years, we will see that we will see all the tendencies for all 4 years. I can really quickly show you how it looks like. I hope you will see it if I just do that. It's the PDF file, it's Word file, which is provided to you, and you also can see the difference between 1981 2001. And well, the distribution is going to be approximately the same, but you see that overall the values, the SST, they did change, they did increase with the time. But yeah, you are free to go and check it yourself and yeah, with a bit clearly, because well, I just don't have much time. I'm almost out of time. So that was it. That was a bit too quick. I hope you understood something out of it. But yeah, again, like there's a video, there's a PDF, and of course, if you have questions, I'm happy to answer them.
Thanks a lot. Thanks a lot, Daria. I think people understood the tutorial now, right? Yeah, so yeah, we have a few questions for you. I will just upload. Okay, so now, okay. So the first one, thanks for the tutorial, Daria. I didn't know about the Dataplot plugin. Do you use it a lot? And or do you advise to go through another programming language for this kind of plots?
Well, first of all, you're welcome. And well, this plugin, I mean, in QGIS there are so many plugins. Like I think it's impossible to know about all of them, but it does exist, and it has different also types of plots. It's not only scatter plots; it has line plots and bar plots and whatever plots. Do I recommend to use it? I don't think so. If you really want to see, for example, you have data and you want to make sure that, like, I don't know, about some trend, or you just want to see like a specific tendency, whatever, you can do that like quick because you already have data in QGIS. But of course, if you want better plots, better like plots that you can be switched, you know, like tuned and made more pretty and stuff, of course, I would go via Python, for example, because well, QGIS is just not made for that. And also, as an example, in this Data Plotly, I did 4 separate plots. You saw I had for each year, each like 91, blah blah blah. And normally, like in in Python, sorry, you can actually have it on one plot to see, right? And well, or like you can reorganize your data. That you have a data set and you can reorganize it, right? And like you have different plots. Well, and here in the Data Plotly, right? Yeah, it's not very flexible. So I would think that Python would be better, yeah.
Okay, yeah, makes sense. Thanks. Okay, so this one, Hello, thank you for this presentation. My question is about the period date of the data. The data is available from 1990 to 2021 for the whole Mediterranean Sea. Is the data available? Okay. Yeah, I guess it was a long data set you used, but yeah, most of the data on the Mediterranean Sea are at least 30 years, I would say.
Yeah. Yeah, there's even like right now I'm looking at the same product at Copernicus Marine Service platform, and I see that it is specified that it's from January 1987 to August 2025. Yeah, we are September, so we are updating regularly, and yeah, so this data available for the whole period and even longer if you need.
Yeah. Thanks for the clarification. Okay, this one. Where can we find the main vectorial and raster layers?
Well, both of them will be provided to you on a platform, I assume, with the tutorial itself. But also, yeah, like in a PDF file, there is links to both, to like Copernicus Marine Service for the main product, and for the external vector layer. It's also there's a link to the original producer.
And yeah, when you download the tutorial for the participants, so all of the files that are used are on the directory, so you should be able to find everything you need to do the tutorial. Another question: when you used the raster calculator, there were changes in the color of the Mediterranean Sea. Is there a way to put a legend scale next to it so that we can have idea what values do those colors mean?
Yeah, of course. For each layer, for each raster layer, there is well, legend, as you said, a color bar for each layer. It's usually just hidden because it's like you can see that there's a little arrow next to each layer, and when you click on it, it actually opens up and shows you the color bar. And when I was showing you the change between all the years from 91 to 2021, they were all on the same scale. So the scale was the same. I think it was something like probably, I can check. It was from 15 to 25. So you could see that, yeah, if it was very red, it was more than 25, and well, below 15 doesn't really go that much, but yeah. So yeah, of course. And also, yeah, you can import images of you can just do screenshot if you want, but you also can export like a frame of your QGIS of map, and it will have also the color bar next to it.
Okay.
But well,
Okay,
it's another tool, yeah.
Yeah, because I think we also had this question. So yeah, this one about the temperature scale when you export the image. So it's also yes.
Yeah.
Okay, so another question about the plugin you show, how to export the graph from Dataplotly plugin. Is there also a way to extract data point into other format, like into a CSV file?
For the first part of the question, yes, from Dataplotly plugin, there is a little button that allows you to save it as a PNG, I think, or I think you can choose. And this is also included in a tutorial. In a PDF and in a full video. I didn't have time, so I didn't explain it. So yes, you can. And for the second part, yes, you can extract data points. It's not a part of a Dataplotly plugin. It's a part of QGIS itself. When you have vector layer, which has some values in its attribute table, you can right click on this layer and export it as, and then you can choose. And for the vector layer, you can choose to export that data in a CSV file. Yes.
Okay, thanks a lot. Another question. What was the depth included in sea surface temperature? Could it be set, or is it automatically based on the data from the master file?
The depth was the surface. It was surface level. So I think it is usually in the products on Copernicus Marine Service. Surface means 0.5 meters, so 50 centimeters deep.
Yeah.
And could it be set? I mean, you have to think about it in advance when you download the data. So when you download the data from the platform, you choose which depth levels you want. I just choose one, so I had only one, but you can select many of them, and then perform your analysis accordingly if you have different levels.
Yeah, it's the file will just be easier if you have several
exactly.
level.
You will have one more dimension. It's not going to be like, how to say that, like 3D, not only longitude, latitude, and data, but also like it will have several sub layers because it also have depth, so you can choose which one you want.
Yeah, definitely. Okay, this question, I'm not quite sure what's the reference. What was the purpose of going to the joins tab?
The purpose is just to have one final layer, because as I told you, the zonal statistics to be calculated, you can calculate it only for each layer separately. So for example, I calculated for 4 years, for different years, and we had 4 separated layers. And going to join tabs was just to show you how you can merge some columns, like specific columns you want from different vector layers to one new layer with all this data. For example, if you want to export it to a CSV.
Okay, thanks. So yeah, we have time for 2 more questions. So yeah, almost the last one. Thanks for the presentation. What does exactly subtract one layer to another layer, like an average?
No, it's just a layer
Subtract.
minus another layer.
Yeah.
Just a difference. So basically what it does, it compares values in each pixel, well, in corresponding pixel, like you have 2 layers, it takes this pixel, and does the subtraction and plots it.
And the last one, so is it possible to add velocity vectors for current maps on QGIS?
Yes, it is possible. Yes, if you have a current variable from the platform, yes, you could do that. It has some specificities to do so. So, for example, with a plugin that I showed you that's been developed here in Maltese, you can have there is an option to do that quite quickly and user-friendly. And I didn't add this into this tutorial, but if you look through other tutorials on Copernicus Marine service platform, you will find that there are tutorials that do work with currents, and there it is explained. So,
yeah, that's what I was going to say. We have plenty of QGIS tutorial on the website, so we will put the link on the chat if you want to take a look. Thanks again, Daria. That's the last question for you. So thanks again for the presentation and the tutorial. And yeah, we will go to the last tutorial of today with Simon. So for the RStudio tutorial, welcome, Simon.
Hello, everyone.
And you can share your screen when you're ready.
Yes. Do you see my screen?
Yeah, we can see it. Thanks.
Okay. So my name is Simon Millet. I'm scientific engineer at Novartis in France. And today you will use a Jupyter Notebook in R to see the evolution of Storm Alex. So first we will do a basic plot, a map. Then we will do a quiver plot of wind. Then we will visualize the wave variation during the storm. Then we will analyze the precipitation flux. And finally, we will study the water column temperature evolution. So this training focused on Storm Alex, which affected southeastern France and part of northern Italy in October 2020. The storm Alex is known for its rainfall that was destructive. So in this training, we will see the storm thanks to the wave, wind, sea temperature, and precipitation fluid over the time. So the Jupyter Notebook must be set up with all necessary libraries. So here it is all the libraries that we have necessary for work. So there is a ggplot2. It is for creating graphic. Dplar, it is a library for manipulating data. rColorBrower, it is for color palette. In plot, netcdf4, it is a library interface for netcdf file format. GridExtra, it is for arranging multiplot on a page. Lubedate, it is a library for date-time data. Scrolls, it is a library for map data to aesthetic. ggquiver, it is a library for creating quiver plot. And Magic, it is a library for image processing. So first we load all the libraries, and if you are using another support, you can download all the libraries thanks to this command line. So this notebook will use the data from the Copernicus Marine Data Store. You have a link here. You can explore all the product and with many filters to select the region or the parameters or the time that you want. For this string, we will use 3 different datasets. There is the Mediterranean Sea physics reanalysis, the Mediterranean Sea wave reanalysis, and the global ocean hourly surface wind and stress. So the period, it is daily for the sea physics reanalysis, hourly here and hourly here. And it is to the end of September to the middle of October 2020. So the files are already downloading in this training in the folder data here. But if you want to download, it is possible. You will need your credential, username and password, and you can try if you want. So first, we will work with wave data. So we will set the path of folder. Here, we load the netcd file with the function nc open, and you can see the information about the netcd file format. There is 3 variables. Here it is the peak period. Here it is the significant wave height, and this variable, it is the wave direction of the wave. And there is 3 dimensions: time, latitude, and longitude. And here it is a global attribute to have more information about the dataset. So first we load all the variables. So latitude, longitude, time, wave height, peak period, and the mean direction. It is possible to have information about the variable, for example, the wave height, to have a dimension. So you can see the dimension, it is longitude, latitude, and time. And to have the value for a single longitude, single latitude, and time. So for example, it is here 3.6 meters. We can do the same for time, for example, but here you can see it is a number, not a date. So to convert the time variable to a date, we use the function asPOSIX. We put the time variable and the origin. Here it is in January 1970. So the origin, it is noted in the characteristic of a netcd file form, netcd file. It is noted here, but is in second since January 1970. So you can run the sale, and you can see now it is a date. So now we will make a basic plot of a map of a wave. So first we determine the figure size. Then we create a data frame of significant wave height dependent only of longitude and latitude. So we select index of time. Here it is this index. So you can see, so we run the sale, and you can visualize the data frame here, but the wave height dependent only of the longitude and latitude. And now we will plot a map of wave. So we use ggplot. we add the value of wave height thanks to geomtile. We put the data frame, we put the longitude and latitude, the coordinate, and then we put the value of wave height. Here it is the color scale option. So here the color, the name of the color bar, the limit if we want. Here there is no limit. And here the NaN value, it is in gray, so inland, for example. And finally, it is general aesthetic option, the title, subtitle, the size of the legend. Here it is adjust the size of the color bar, and here to maintain the proportion between longitude and latitude. And here we save the figure in the folder figure, and the name of the figure, it is basic figure. So we can see the map of the wave height in October 4th at 5 a.m. So you can see that the waves are higher here in the south east of coast in France, and it is higher than 3 meters. So now we have seen how to make a map of a wave. It is interesting to know the direction. So for this, we will use the wind. So we do a map of wind with arrow to see the intensity and the direction of wind. So first we load the data set. So it is exactly the same code that you have seen before. But you can see that the variable of wind, it is eastward and northward wind. So we convert here wind in norm, and we create a data frame exactly the same that you have seen before of a wind variable dependent of longitude and latitude. So you can see the data frame here, longitude, latitude, the eastward, northward wind, and the norm of the wind. Here we create another data set, especially for arrow visualization. It is based on the original data frame, so this one, but we reduce the number of points to make the arrow visualization clearer and more readable. So we have a value of wind each 0.25 degrees of longitude and latitude. So we use the original data frame here, and we keep only by each 0.25 degrees. So you can see the new data frame here. That is, you have all the variable, and here it is each 0.25 degrees. So we can map variable. So it is approximately the same code that you have seen before, but we add the geomquiver function here. We put the new data frame, and we put the eastward and northward vectors. So the map shows the wind. It is the same date that for wave we have seen before. The direction of wind is in the southwest, and the wind is more important in the same space that wave was higher. So now we will work again with wave variation, but we will see a map for each day of the storm. So first we select the index of time. So the index of that we want to plot, it is a daily map at midday. Then we create a data frame along the spatial and temporal coordinate. Then we plot the map for each day, and finally we generate an animation to see the variation of wave during the storm. So first we set the index of time. So it is for each day at 12 p.m. We create a data frame. So here it is dependent of longitude, latitude, and time, and we and the time it is only for this index. So you can see the data frame, longitude, latitude, time, and the wave height. Yeah. To simplify the code, we create a plot function. The name is mapping data frame. So you can see here it's approximately the same code. And here we do a loop of the data frame to create a map. And the map are saved in the figure here, figure for GIF here. And then we will create a GIF animation. So we select the folder where there is all the figure, and we sort to do in the good way. And we can run the animation, and you can see here the animation of wave. So it is a map for each day. And we observe that the waves are highest after the storm pass around in October 3rd, with the wave height is above 3 meters. Now we will see the precipitation flux. So to do this, we will open the file and then plot for different date. So we load the variable. We identify the index of time for each day. We create a plot function here. It is approximately the same function that you have seen before, but leisurely different. And then we create the map for each day in variable P1, P2, P3, and P4. And finally, we, thanks to the function grid arrange, we put all the map in the single figure. And you can see here the 4 map for the for different time. And you can see that the precipitation is very low on the 1st of October and in the 4th of October. And principally is very intense in the 2nd of October. It is higher than 4 millimeters per hour. It seems low, but it represents an average of 4 millimeters per hour over 24 hours. So it means over 80 millimeters in a single day. So it is very large. So it is for this the storm Alex caused many damage because of precipitation. And now we will finally see the temperature evolution during the storm to see the impact of storm Alex. So first here we load the variable of temperature. We will look in the variation at a second point. So it is near Nice in France. So here it is the coordinate. And here we search the nearest coordinate to do the difference. And the nearest coordinate, it is this one. So it is this coordinate that we have work. We create a data frame. So it depends of depth and time because we choose this coordinate. So it is possible to see the data frame here. It is dependent depth, time, and you have temperature. And here we create a regular vertical grid because the depth is not a regular grid, yeah, and we have a blank when we plot the map. So to do this, we create a regular vertical grid each meters, and then we interpolate the value of temperature to have a grid, in regular grid each meters. So here it is the data frame. And finally, we plot the temperature. So the sea temperature that is dependent of depth here and the date. And you can see there is a high temperature before the storm. And in 2 days, there is a drop of sea surface temperature and mixing of water during the storm. So the storm has an impact on oceanographic parameter. It mixing the water and during the passage of the storm decrease the sea surface temperature. So now the training is finished. Thank you for your attention. And if you have some questions, do not hesitate.
Thanks, Samuel, for the presentation. So yeah, we have a few questions. So I will just upload this one. So the first one is also a comment, but I will read it whole for everyone. So in R, there is a much better package to work with NetCDF data. And CDF-CF, it actually interprets the CF attributes of the data set. Time management is automatic and subsetting can be by real values rather than indexing the array. Have you considered using this package?
It is possible to use this package. I want to use another package to see different view and different possible, but it is possible to use this package. It is good too.
Okay. Yeah, maybe at one point for one tutorial we could use this one to
Okay.
test. Yeah,
Yes.
we can try just to show all the possibilities.
Yeah.
Okay, thanks a lot. So this question and more open questions. Thanks for the tutorial. Does the storm have an impact on other parameters than the temperature, I would say?
Yes, the storm have an impact of, for example, salinity, because the storm mixing the water, so mixing the salinity too, and the turbidity too, because there is many the river runoff entails an increase of turbidity. So there is many parameters that is impacted by the storm. The principal is temperature, salinity, and turbidity.
Okay, thanks. And yes, so these parameters are also available on the Copernicus Marine website.
Yes.
So yeah, if people want to study these parameters, it's also possible. And you can just reuse the tutorial, I guess, also, and just change a few things to study the salinity or turbidity.
Yes.
Okay, I'm just adding this one. So thank you for the tutorial. What can you say contribute to the rise in precipitation on October 2nd?
In October 2nd, the precipitation is more important because I don't understand very the question.
Yeah, I guess just why there was a lot of precipitation at this date. So I don't know, maybe it was like way hotter a few days where the temperature were warmer a few days before. So maybe it causes a lot of evaporation and then it rained?
Yes,
But you didn't look, so
the Mediterranean Sea in October was very warm, and when there is a storm with the air temperature is low, there is many evaporation because many evaporation and the precipitation was very intense. It is now in Mediterranean Sea every autumn, and in October 2nd it is the date where the storm is in this area, and because of the mountain it is blocked, and the precipitation stay in the same place and is very intense.
yeah, definitely. And yeah, the Mediterranean is also often way warmer than it should be in summer and early autumn. So yeah.
Yes.
For this one, so yeah, still a question about R or Python. Is it better
Yes.
to work the NetCDF data with R or Python, or it's only the preference?
It's in my mind, it's only a preference, but here is used for statistic, principally for statistic manipulation. But Python now is very used in the community, and I think it is easier to work with Python because the community is large, and if there is question, there is many people to answer more than in R.
Yeah, I would have said that also. So yeah, definitely for the help you can find on internet. Okay, so yeah, that was the last question about the R tutorial, Simon, I think. Yeah. So yeah, thanks again for your presentation, and yeah, I think people
Thank you.
quite enjoyed it also. So okay, so thanks again to everyone for their presentations, and to the participant for the participation, obviously. So yeah, we are reaching the end of today's session. So just to tell you again, you can find the tutorials on the website along with the full video demonstration of the tutorials, and you will also have the replay of today, obviously. And yeah, so speaking of replay, they should be available today, so you will receive an email notification. And just before you leave, we just want to remind you that there is a section next to the Q&A section reserved to the polls. So yeah, if you have 2 minutes of your time to give us your feedback, we would really appreciate it. And yeah, we will let you know by email once the replays are available, and you will also receive a certificate of attendance along this email. And yeah, thanks again to everyone for their presence, and we'll see you in the next training. Bye.